All righty, welcome back everybody to chapter 4. We're going to slog through to the end of this chapter. Got a lot of redox to do. So we're just going to start right off with balancing redox reactions. The thing we really want to start by doing is figuring out our oxidation numbers and then splitting our chemical equations into half reactions. One of the half reactions will be based off oxidation, and the other one off reduction. By the time you're done balance, so this whole chemical equation right here is a redox chemical reaction. By the time you're done balancing this, not just atoms should be balanced, but you should also have balanced charges and balanced electron exchange. And so we'll start working through that to see what that looks like. So let's just look at breaking things apart into half reactions to start with. So we're going to need our oxidation numbers. So you see here silver metal. That's a common elemental form. So that has a charge of 0, an oxidation state of 0. The other common elemental form on here is hydrogen gas. So that also has a common state of 0. Now, let's look at hydrogen sulfide gas, H2S. Okay, we have hydrogens, so remember our rules. So I can say each hydrogen is a +1. There are 2 hydrogens. Oops, not minus. Which means that gives a total charge of +2. To be neutral, that now means that my 1 sulfur has to be a -2 in its oxidation state. You could have also done that by saying, sulfur is in the oxygen group, and that group, column 16 on the periodic table, gets a common charge of -2. Uh, yeah, so the next you see we have silver sulfide. You again have 2 atoms that have common charges, but we can still figure it out. We can say, well, sulfur has a common charge of a -2 based off being in group 16. Now, for this to be neutral, I have 2 silvers. And so whatever silver is, when you multiply it by 2, it has to give you a total charge of +2. So that here, when you have 2 minus 2, you get a charge, so +2 minus 2, you get a charge of 0, or a neutral molecule. And since I have 2 silvers, that means each silver has to be a +1. But you also remember silver is a common charge, and it is going to take a +1. But still, you can go through and you can figure it out. Now we have to break this into half reactions based off oxidation and reduction. So we notice that silver goes from a 0 to a +1. So it's oxidized. Oxidized. Hydrogen is going to go from a +1 to a 0. That's reduced. So my first half reaction is going to be my 2 silvers. And then that's going to go to the silver sulfide. This is my oxidation half reaction. My other half reaction is going to be reduction, so it has to be the hydrogen species. And so for reduction, I'm going to take my hydrogen sulfide gas, and then it's going to yield hydrogen gas. And I get that, like, for the reduction half reaction, I don't have a sulfur on the right-hand side. I get that. But we'll deal with that as we start going through and looking at the rules of how to balance uh, redox reactions. Right now, we're just worried about splitting this apart into an oxidation half reaction and a reduction half reaction. So again, you find the oxidation states on your individual atoms, and then you're going to take the species involved in oxidation, and they get their own half reaction, and then you're going to take the species involved in reduction, and they get their own half reaction. Okay, so now there's going to be three types of balancing that we're going to do. Here you see balancing a simple redox reaction. I have worked on this for a number of years, breaking these down into steps. So when you're working on this on assignments or on exams, you need to know these steps and you need to follow them. And so again, they're meant to be done in order. So you do step one, then step two, then step three, so on and so forth. So these steps will help you really get a grasp of balancing redox reactions. You'll be happy for them when we get to redox reactions in acidic solutions and redox reactions in basic solutions. So first here, for our simple redox reactions, you see we're going to assign oxidation numbers. Then we're going to separate our chemical reaction into half reactions. Then we're going to find the number of electrons needed for each half reaction and add them to the positive side of the half reaction. So we're going to be using electrons to balance the charges. So in this case, electrons are seen as a -1. And so that's how we're going to use them. Then we're going to balance the electrons by multiplying each half reaction by an appropriate number. So, like like for example, our oxidation half reaction might need 6 electrons. That means our reduction half reaction needs 6 electrons. Then we're going to add the chemical equations, our half reactions together to get the overall balanced redox reaction. All right, let's look at a simple redox reaction as an exercise. So here you see we have aluminum reacting with copper 2, and that ends up producing the aluminum ion. Remember, it's not aluminum-3. Aluminum is a metal, yes, but it's a main group metal, and it's in that, was it 13? Yeah, it's in group or column 13 on the periodic table, which if you're counting over, remember your group 1, group 2 are +1 and +2 for their ions. You skip the transition metals, and then you go to group 13, and that's your +3 column. So make sure you're still remembering how to do your charges of common charge ions, but based off their position in the periodic table. And then we end with solid copper. So you can see that definitely electrons are changing hands. That's what redox is all about, electrons being shared back and forth. So here, aluminum, oxidation state of 0. It's a common elemental form, solid metal. Well, that means that copper is also a 0 because it's a common elemental form of a metal. Uh, these are easy. You know that that one's a +2, and that one's a +3. Probably the easiest oxidation numbers you'll assign. Okay, now the half reactions. Well, our oxidation half reaction is solid aluminum to the aluminum ion. Um, you can keep track of your phases all the way through, so at each step, or you can put the phases back in at the very end once you get your final balanced redox reaction. I don't care, just as long as once you get to that final reaction, everything's right. I usually won't carry through aqueous, so I don't have to write it a bunch of times, but I'll carry through solid, liquid, gas, just to make sure I remember which species those go on, because then anything else, once I get to the end, would end up being aqueous. Then my other half reaction is going to be the reduction half reaction with copper. Copper, copper 2 is going to become solid copper metal. Okay, now we need to balance charges. Well, you have to take account of what the charges are on each side. Solid aluminum, that's a charge of 0. that side has a +3. For copper, the left side has a +2 for its charge, 0 on the right-hand side. So this is where I use electrons. And we'll say that was step 1, step 2. Okay, so to balance these, the aluminum, so watch, I'm going to do my aluminum solid. My aluminum ion +3 electrons. Remember, electrons count as a -1. So if I have +3 and then 3 electrons, -1, -1, -1, that's going to be neutral. So now both sides are neutral. That's what we're after. So that means for copper, I'm going to need 2 electrons on the left. Because then that makes both sides neutral. Let's see here. Separating half reactions. Oh, okay. So this one was, oh, I'm just off a number. So step 1 was oxidation numbers. Step 2, step 3. Now we're ready for step 4, which we need to make these balance. So the same number of electrons. So step 4. If you look, you have 3 electrons and 2 electrons. Well, those are going to come together at 6 apiece. So we need to multiply these equations by a number that's going to make that happen. Okay, so my aluminum is going to be multiplied by 2. Okay, and when I do that, I'm going to get, how much space do I have? Yeah, I have plenty. So that's going to give me 2 aluminums, 2 aluminum ions, and then 6 electrons. So when you multiply a chemical equation, the number you multiply it by distributes through the whole chemical equation. Well, so then what's copper going to need? Well, it's going to need to be multiplied by 3. All right, so that's going to give me 3 copper 2 ions, 6 electrons, and then 3 coppers. Now, I want to, I'm going to take this half reaction and this half reaction and add them together. Okay, so that's going to be 2 aluminums. Let's see. And those are solid. I carry solid through. Plus 6 electrons. Okay, and then I need the 3 coppers plus 3 copper 2 ions. And those are going to yield 3 coppers. Now, I'm going to go ahead and bring everything down on this one. I won't do it on later ones. I also don't care if you just say, at this step, if you say, well, I don't want to write the 6 electrons again. So I'm going to say, well, there's 6 electrons on the left, 6 electrons on the right. You can do either one. You could also make it look like this, where you go, well, when I add these together, I'm going to get two aluminums, plus three coppers, copper two ions plus six electrons. It's going to yield two aluminum ions plus three solid coppers plus six electrons. And then from here to finish it off, you say, well, six electrons and six electrons is the same. And now my answer for this, two solid aluminums. And you see here, I'm putting all the phases back in for the final answer. You're going to want to make sure you do that. So again, you could either carry them all the way through or just make sure you get them correct at the end. Two aluminum ions. Plus three coppers. Now, this is not intuitive because if you go back up to the very beginning, this looks like a balanced equation because you have one aluminum, one copper, one copper. Well, that looks balanced. Yeah, but the electron exchange and charges aren't balanced. So again, so if I look at this very first equation, you see if I add up the charges on the left, I have a 0 and a plus 2, so this whole side is plus 2, this whole side is plus 3. Well, charges don't balance. The aluminums exchange 3 electrons, the coppers exchange 2 electrons. It's also not balanced. So by the time I get to the end, if you look here, the aluminum and solid aluminum, solid copper are still 0, but I have 3 copper 2s, so that's going to be plus 6. I have 2 aluminums, so that's going to be a total charge of plus 6. So the charges are balanced. And with these coefficients, now the aluminums and coppers are each exchanging 6 electrons. So now everything is balanced. The atoms are balanced, the charges are balanced, and electron exchange is balanced. That's the whole goal to redox. All right, the next one now. Now we're going to step it up. And now this is in the textbook, but I always make sure to go through this in detail because, as I said, those of you who are going on to like your microbiology, uh, I know at least microbiology. I'm not a biologist, so maybe immunology. I'm not sure, but you're definitely going to need your redox. If you do anything like materials engineering, you're going to need redox, and it's usually going to be in one of these types of solutions, acidic or basic. Now you have slightly expanded steps. So you again start by assigning oxidation numbers and then two separate into half reactions. Then you're going to look at your half reactions. And if in any atom other than oxygen or hydrogen that's not balanced, you're going to use coefficients to balance them. Then you're going to go and you're going to balance all your oxygens by adding in waters. Once you add all your waters, you're going to balance your hydrogens by adding protons. Then you're going to go back to, I need to balance the charge on each side by using electrons. You're going to scale the half reactions so the electrons match. And then you're going to add your equations together and cancel out like terms on either side of the equation. Okay, so here we have manganese 2, NaBiO3. Let's see, then bismuth, sodium, and your permanganate ion. That's one you should know from your polyatomics list. Okay, so see, looks quite a bit more complex. Let's just start with our oxidation numbers. Some of these are straightforward. That manganese is plus 2. This bismuth is a plus 3. This sodium is a plus 1. Let's do permanganate. Now we know that each oxygen is a minus 2. And when I have four of them, that'll give me a total charge of -8. Now, whatever manganese is, it has to be a positive number that when added to -8 leaves a -1. So it has to be a +7. Uh, 7 minus 8 equals -1, which is that charge right there. Okay, let's do our compound on the left side. Again, we can start with oxygens. Each one is a -2. Three of those oxygens is going to be a total charge of -6. Sodiums are a +1. Now, if you were in class, I'd make you tell me why, but you're not here. So remember, that's because sodium is in group 1 on the periodic table. That whole column, your alkali metals are your common charge of +1. Now, bismuth. I have a +1, I have a -6. Whatever bismuth is, it's going to have to add to those two numbers to make 0, because this is a neutral compound. So then bismuth has to be +5. And now we can see our redox atoms. Manganese is oxidized, and bismuth is reduced. Okay, so our half reactions. Remember, this is a +7 manganese. Make it stand out a bit. And then bismuth is going to be the base of our other half reaction. And what I'm going to do, since the left side has sodium in it, I'm just going to grab the bismuth, uh, very solid through, and the sodium ions. Again, that's a little intuition. You'll pick up this intuition as you practice these. I do expect to see you go through. I do expect to see most of your work, or all of your work, as you're going through these, because again, I'm not grading your final answers. I'm grading your logical process. I have to see what it is and where it's good and where it's bad. Okay, the next step. Now, remember, one of those steps is balance every atom other than oxygen and hydrogen. Well, that's already done because you see there's one manganese, a sodium, a bismuth. So that we can just, a lot of times you'll skip that step because it's already done, but if it's not done, you want to make sure you do it. So now we're going to start to balance oxygens by adding waters. So look at the manganese equation. You notice how you have four oxygens on the right, none on the left? That means I need to put four waters on the left side. And carry liquid through. And you'll notice that balances the oxygens. Then for the bismuth half reaction, I'm going to need three waters on the right because of that three right there. Okay. Now the next step is going to be using hydrogens or protons. So look here, protons to balance all the hydrogens that I just put in. Okay, so let's look. The manganese equation has 4 waters on the left. That's going to be 8 hydrogens. So that means I need 8 protons on the right. And you'll notice that bounces the hydrogens from the water. All right, now the sodium, the bismuth equation, you notice that I have 3 waters, which is going to mean I need 6 protons on the left. Now my hydrogens are balanced. Now I'm going to need to use electrons to balance out charges. So let's see what we have here. Okay, so my manganese equation, I have a +2 and neutral. So this whole side is +2. My manganese, I have +8 -1. So that means my right side is going to be a total of, let's see, +7. What about my bismuth equation? Well, I have a neutral and a +6. So this whole side is +6. Then I have a +1, +3, and neutral. So that means this whole side is going to be a +4. Okay, so for my manganese equation, I'm going to need 5 electrons on the right. Because if you think about it, that's going to be +7 -5. So the 5 electrons equals +2, which equals the left-hand side. And then for my bismuth equation, I'm going to need 2 electrons on the left to take that +6 down to the +4 that you see on the right-hand side. Okay. Okay, so the manganese equation, there's those electrons, and then the bismuth equation. Okay, now charges are balanced. Now you notice that we have 2 electrons and 5 electrons. Those are going to come together at 10. Really what you're looking for is the lowest common multiple for your electrons. So that means that my first equation has to be multiplied by 2. And that's going to give me 2 manganese. Let's see, 8 waters. 2 permanganates, 16 protons, and 10 electrons. Now, my second equation is going to need to be multiplied by 5 to get to 10 electrons. And that's going to give me 5 of these, 30 protons, 10 electrons, 5 bismuth, 5 sodium, 15 water. Now what I'm going to do next is take this equation and this equation, I'm going to add them together to get an overall reaction. All right, so let's say we're going to take, it's not good, this here. That equation there. Then we're going to add these chemical equations. Now, before the last time I brought down the electrons, this time I don't care. Like the 10 electrons on the left and the 10 electrons on the right are going to cancel. Let's bring everything else down and see what we have. Okay. 2 manganese 2s. 5 with my bismuth compound. Eight waters. 30 protons. The other side. 2 permanganates. 5 bismuth. 5 sodiums. Let's see. 15 waters. And 16 protons. Now, I want to cancel out like terms on the left and the right. So first, I have 8 waters, which are going to cancel, because then these 15 waters on the right, that's going to become, so 15 minus 8 is 7 waters. Then I have 16 protons that'll completely cancel from the right, and this 30 will become 14 protons. And that's everything that I can cancel. So then we get to the final answer. And since it's the final answer, make sure your phases go back in. Let's see. Plus 14 protons. These will be aqueous. Let's see, then the 2 permanganates. 5 bismuth. 5 sodiums. And then 7 waters. Alrighty. And there we go. There's your final answer. And so this is redox in an acidic solution. See, that's why I've broken these down into steps. And you're going to want to follow the steps because when you're in acidic solution, you want to make sure you're ending with extra protons in the solution. And so now we're going to do another one of these just to make sure you have the hang of it. So I would suggest stopping the recording and trying to do this, work through it on your own and see how far you got. But we're going to go ahead and work through it. All right, so here we have a dichromate reaction. Dichromate with chloride is going to give chromium-3 and chlorine gas. Well, the first thing is, of course, the oxidation numbers. So if every oxygen, again, is a -2, 7 of them will be a total of a -14 for its charge. Whatever chromium is, 2 of them is going to have to give a +12 to make sure I leave an overall -2. So that means each chromium will have to be +6. This one's easy. That's a -1. This chromium is a +3, and this chlorine is a 0 because chlorine gas is the common elemental form. Okay, half reactions. Dichromate. I guess that's the reduction half reaction, doesn't matter. Or that chromium is a +6. The oxidation half reaction is going to be chloride to Cl2. Now you can actually do step 2, where you say, oh, I have to balance everything that's not oxygen or hydrogen. Because you notice how I have 2 chromiums here and 1 here, 1 chloride and 2 chlorines. Well, I have to balance that. Okay, so the next step is going to be Cr2O7, no, 2 minus, 2, 2 minus, there we go. Let's see. 2. Now I have 2 chromiums on each side. And then I'm going to do 2 chloride for the Cl2 gas. Now it's time to start balancing oxygens and hydrogens. Well, we're lucky in the chlorine half reaction, there are no oxygens. So we don't have to deal with it. We just have to deal with the 7 oxygens in the dichromate half reaction, okay? And because there's 7 oxygens, I need 7 waters. The chlorine equation stays the same. Okay, now I need to use protons to balance hydrogens. Well, chlorine has no hydrogens, so that half reaction can stay the same. Okay, so what on the right, I have 7 waters, which is going to be 14 hydrogens. So I need 14 protons on the left. And then the chlorine equation is still the same. Okay. So now I'm going to need to use electrons to balance charges. Let's see what we have. My chlorine equation, well, the chlorine gas is a charge of 0. The two chlorides is a charge of -2. So each chloride is a -1. Okay, so my chromium equation, waters are neutral. And then the two chromium 3s is going to give me a +6 on that side. And then I have +14 from the hydrogens and -2, +12 overall. Okay. Now what that means is to make these match, my chromium equation is going to have to get 6 electrons. I take that +12 to a +6, and then 2 electrons there to take the 0 to a -2. Okay, so that next step, okay, so now charges are balanced, hydrogens are balanced, oxygens are balanced. So then my two chlorides, that is going to give me chlorine gas plus 2 electrons. Well, we're lucky because if we want these electrons to match, all I have to do is multiply the chlorine equation by 3 to make both of them, both half reactions, have 6 electrons. I'm just going to bring this equation down. And then I'll need 3. Let's do 2 chlorides, Cl2 gas, 2 electrons, multiplied by 3. That's going to end up giving 6 chlorides, 3 chlorine gas molecules, and 6 electrons. So now I'm going to add this half reaction to this half reaction to get my overall reaction. Alrighty. Alrighty. So we see 6 electrons on the left and right cancel out. Let's go ahead and bring everything else down. Dichromate. 14 protons. 6 chlorides. Let's see, 2 chromiums. 7 waters plus 3 chlorine gases. And we look and we say, well, can we cross anything else out? And no, we really can't. So that means that our final answer is going to be that. So there's our final balanced reaction, redox reaction in an acidic solution. Again, acidic solutions need to end with an excess of protons. Okay, on to the next one. Balancing redox in basic solutions. It's going to be pretty much identical, except you have an extra step. So you assign oxidation numbers, separate into half reactions, balance elements other than oxygen and hydrogen, use water to balance oxygen, protons to balance hydrogen, uh, balance the charges in the half reactions by using electrons, scale the half reactions so that you have the same number of electrons in each. Then you're going to want to add the balanced half reactions together to form your single overall chemical reaction while canceling the electrons on both sides. Now here's your new step. Then you're going to add hydroxides to balance out the protons that are in the equation. You're going to want to look for the side that has the most number of protons, and you're going to add that many hydroxides to each side. Then you're going to combine hydroxides and protons to form water molecules and cancel common terms. So what you're going to end with is, just as your acidic solutions ended with an excess of protons, your basic solutions need to end with an excess of hydroxides. If you end a basic solution balance with protons in your solution, you need to do it again. So if you go into basic solution and you get protons, you're going to have a bad time. All right, so this is easier to understand if we see it firsthand. So here's a nice reaction to look at. The first thing we need is oxidation numbers. Well, nitrogen. Nitrogen is in column 15, so it is a common charge of -3, which means carbon has to be a +2 because we have an overall charge of -1. Permanganate. Oxygens are a -2. 4 of them is a total charge of -8, which means that the manganese has to be a +7. The CNO ion. So oxygens are a -2. Nitrogens are a -3. I have a -2, -3, which is a -5. Carbon is going to have to be a +4 because +4 -3 -2 leaves a -1. And then the manganese 4 oxide. Each oxygen is a -2. 2 of them is a total of -4. And since this is a neutral molecule, manganese is going to have to be a +4. All right. So if we look here, carbon goes from +2 to +4. So carbon is oxidized. That'll make one half reaction. Your other half reaction is going to be based on manganese because it goes from a +7 to a +4, which means manganese is reduced, which would make the permanganate the oxidizing agent and the cyanide the reducing agent. Okay, so first half reaction, cyanide ion goes to CNO. Your reduction half reaction, your permanganate is going to go to the manganese 4 oxide. So what we have a +2, carbon over here is a +4. Manganese on the left is a +7, and on the right it's a +4. You don't necessarily have to write that in. I just write that in so that I'm keeping a check on myself to make sure, yeah, I've got the right half reactions. Okay, so Now, next, we would be balancing atoms other than oxygen and hydrogen. However, that's already done. Carbon, carbon, one nitrogen, one manganese, one manganese. Okay, so now we can just move on to using water to balance oxygen. Okay, so your oxidation half reaction is going to get a one water molecule on the left due to the one oxygen. Oxygens are balanced. Now look here. Let's see, we have four oxygens on the left, two on the right, which means that the right-hand side of the manganese equation is going to get two waters to give both sides four oxygens. Okay, now I need to use protons to balance hydrogens. All right, so let's see what we have. Well, I have two hydrogens on the left side of my cyanide equation. That means I'm going to need two protons on the right. On my manganese equation, I have two water, so four hydrogens, which means I'm going to need four protons on the left. All right. Okay, so cyanide, water, cyanoxide. That's not a proper name. That's just me talking generally. Let's see, plus the two protons to balance out the hydrogens. Now for the permanganate, the manganese half reaction. There's my permanganate, plus the four protons that I need. Manganese 4 oxide, plus the two waters. All right, now oxygens and hydrogens are balanced. We need to use electrons to balance charges. So what are those charges? Well, if we look at let's look at the cyanide equation. Cyanide is a -1, water is neutral, so that's a total charge of -1. Cyanide is -1. The two protons are +2, so -1 plus 2, giving an overall charge of +1. Okay, so that means I'm going to need two electrons on this side to make both sides a -1. Let's look at the manganese equation. I have a -1 and a +4, total charge of +3. And I have 0, 0, so total charge is 0, which means I'm going to need three electrons on the left to make both sides equal 0. Okay, so we're going to get cyanide plus water. That's going to yield CNO plus two protons plus two electrons. Now the charges are balanced. Permanganate. Okay, so we're going to need permanganate plus the four protons plus the three electrons. And that's going to give manganese 4 oxide plus 2 waters. Now charges are all balanced. Okay, so what do we have? We have 2 electrons and 3 electrons. The lowest common multiple of those two is 6. So take this equation here. Multiply this one by 3 to get 6 electrons. Okay. Multiply that in. 3 cyanides, 3 waters, 3 CNOs, 6 protons, and 6 electrons. My second equation, my manganese half reaction, to get to 6 electrons, I have to multiply this one by 2. All right. Permanganates plus 8 protons plus 6 electrons. It's going to give me 2 manganese oxides. Not a proper name, I'm just getting tired of saying it. 4 H2O, 4 waters. Now, I'm going to take this equation and this equation and add them together. Oh, I still have plenty on. Okay, so put that one there. Grab this one. Okay, now we're going to add. Well, the first thing we're going to see is 6 electrons are going to cancel. Now, we are not going to cancel anything else until we get through the hydroxide step. Okay? All right. So, 3 cyanide, 2 permanganate, 3 waters, 8 protons, 3 CNO, 2 manganese oxide. Let's see, 4 waters, and then 6 protons. Okay, now let's take a look. You notice how we have 8 protons on the right and 6 on the left and 6 on the right. Okay, so we want to make sure we add enough hydroxides to get rid of our protons, which means each side of the equation is going to get 8 hydroxides. When you're done, you'll notice that you have no hydroxides left on the left, and you'll have hydroxides excess on the right. So we need to put that 8 hydroxides on each side. We might need more room than that. Now we're going to look. You see the 8 protons and 8 hydroxides? That's going to give me an extra 8 waters. And so when I add 8 to 3, that'll give me 11 waters. On the right, I have 6 protons, 8 hydroxides. This will give me 6 waters plus 2 leftover hydroxides. Okay, and so then this 6 added to that 4 will be 10. So now we're going to do that. So what, 11 waters? On the right, 3 CNO, 2 MnO2, 10 waters, and 2 hydroxides. Now we're going to cancel like terms. Okay, I have 10 waters on the right, 11 on the left. So the full 10 on the right is gone. That's going to become 1 water. And that's all that's left. So now we can write down our final answer. Okay. Cyanide, aqueous, 2 permanganates, aqueous, plus water, 3 CNOs, it's an ion, so it's aqueous, 2 manganese 4 oxides, waters are canceled out, plus 2 hydroxides. It's an ion, so it's aqueous. And there's our final answer. Yeah, you did it. There we go. That is our final answer. And you'll notice that this is in basic solution, so we ended with excess hydroxides and no protons. All righty. So that was your first basic solution. We're now going to do a second one to practice. See, what I would do in class is this is where I would tell the class to get in groups and try to solve this. So you might want to, pause the recording and try it for yourself, but otherwise, here is uh, redox in a basic solution. Looks a little more tricky, but it's really not. So chromium solid, that's a solid metal, that's standard elemental, so it's a charge of 0. Next, we have our chromate ion, one that you should know. It's on your polyatomic ion list, or you should be getting used to. Every oxygen is a -2, and 4 of them gives an overall charge of -8. Chromium, then, is going to have to be a +6, because +6 -8 leaves -2. Okay, now, here we're going to say oxygen is a -2, hydrogen is a +1, which makes sense because all hydroxides are a -1. And when I have 3 of them, gives me a total charge of -3, which means chromium here has to be a +3 because the whole molecule is neutral. Okay, so there's our oxidation numbers. Now let's split into redox reactions. Chromium in this case is both oxidized and reduced. So let's look at our oxidation half reaction. Solid chromium goes to your chromium hydroxide, your chromium 3 hydroxide. And so chromium goes from a 0 to a 3, so that's oxidized. Your other half reaction, your chromate ion, chromium goes from a +6 to a +3, so this is reduction in the chromium 3 hydroxide. And now that you know the proper name of this is chromium 3 hydroxide, I'm not going to say that every time. So this is how you break it apart. It looks a little confusing because you don't have multiple products, but you can have an atom that undergoes both oxidation and reduction in the same reaction. Second step, balance everything other than oxygen and hydrogen. That's already done because you have a chromium and a chromium, 1 and 1. That's already done. So now we're going to balance oxygen using waters. Yep. You look here, the chromium hydroxide, you have 3 hydroxides, which leaves 3 waters, which means I need, which is 3 oxygens, so I need 3 waters on the left side. Okay, so that's going to be solid chromium, 3 waters, and then the chromium hydroxide. Okay, now in the reduction half reaction, you have 4 oxygens and 3 oxygens. That means your right side needs 1 water. Chromate. All right, now I'm going to balance hydrogens using protons. Okay, well, let's take a look here. I have 3 times 2, so I have 6 hydrogens on the left, 3 hydrogens on the right, so I'm going to need 3 protons on the right. Here I have 3 hydrogens and 2 hydrogens, so I'm going to need 5 hydrogens on the left. All right, now hydrogens are balanced. Next thing we're going to do is use electrons to balance charges, so let's try and figure out what those charges are. For my solid chromium equation, I have solid chromium and water on the left, so that's a total charge of 0, versus on the right, I have a neutral molecule and 3 protons, so a total charge of +3 on that side, which means that side is going to end up getting 3 electrons to make everything neutral. Okay, so let's see. My bottom equation, my chromate is a -2 plus 5 hydrogen, so 5 protons. So it's -2 plus 5, so total charge of +3. And then, of course, the right is 2 neutral molecules, so a total charge of 0. Boy, did we luck out. That means the left side is going to get 3 electrons. You like it when things go this way. Now, this is the point where the next step we would do would be to balance multiply these equations to get the same number of electrons in each one. However, that's already done. So the next step we're going to go to is adding these equations together. Okay, so we notice that the three electrons are going to cancel. All right, so now solid chromium plus chromate plus 3 waters plus 5 protons. Now you notice how I have chromium hydroxide, chromium hydroxide. What we do is now we just have 2 or chromium hydroxides plus water plus 3 protons. All righty, now we're going to look and we're going to say, well, I have 5 protons on the left, 3 on the right. That means each side is going to get 5 hydroxides. I have to go with the highest number of protons. Okay. Chromium, chromate, waters, protons, hydroxides, chromium hydroxide, water, protons, and hydroxides. 5 protons and 5 hydroxides is going to give 5 waters. When added to the 3 waters, so added to those 3 will give 8. These 3 protons and 5 hydroxides are going to give 3 waters and 2 hydroxides. These 3, when added to the 1, will give 4. Okay. No, 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 no. We have 8 waters this time. 8 waters. To the chromium hydroxides. Let's see. 4 waters and 2 hydroxides. And now we're going to say, well, I have 4 waters on the right, 8 on the left. So those 4 are gone. That 8 becomes a 4. So you're just dividing through. If I divide out 4 waters from the right and I divide 4 waters from the left, I'm left with 4 water molecules. So then I'm ready for my final answer. Chromium plus the chromate ion plus 4 water molecules. 2 chromium hydroxides. No water and 2 hydroxides. And that's my answer. Okay, so that is balancing redox reactions in simple acidic and simple, then acidic solutions and basic solutions. And this is going to all culminate to, we were talking about titrations with acid base. You can also do titrations with redox solutions so that you can kind of judge you can judge how much of an ion or something is another volumetric analysis. So down at the bottom here, you see a very common redox titration. Some of your very common oxidizing agents for redox titrations are your potassium permanganate, your potassium dichromate, and cerium hydrogen sulfate. Kind of cut this potassium here. There we go. But let's look at and it's gonna we're gonna solve it a lot of the pretty much like we did the other titration with stoichiometric calculations, but we're gonna need our balanced redox reaction. Okay, so you read through this. And so at the end, it's like, what is the mass percent of the iron in the iron ore that's been mined up? And so what you're doing is the iron ore was dissolved in hydrochloric acid. So this is an acidic solution. And all the iron was reduced to iron 2 ions. So then you're going to titrate this solution with potassium permanganate, one of your oxidizers. That's going to produce iron 3 ions and manganese 2 ions in the acidic solution. You needed 38.37 milliliters of 0.0198 molar potassium permanganate to titrate the solution from 0.6128 grams of iron ore. So we want the mass percent of iron in the ore. Okay, so what is the mass percent of iron in the ore? Let's look at things we were told. Things we know. It's an acidic solution, so we know what our balance is going to have to be. Now, we don't necessarily have an equation to start with, but what we're told is we know that during the process, iron 2 ions will be oxidized to iron 3 ions. And if that's happening and the oxidizer itself is the potassium permanganate, that means that something in the potassium permanganate is going to have to be reduced. And so we're going to have a reduction of our permanganate ion. Potassium is just not going to play a role. 2 manganese 2. Okay, and so then let's see. Remember, our square brackets means concentration, because I'm tired of writing capital M, and we have so many of them, I don't want you to get confused. So this bracket, remember, means concentration, so that it's 0.0198 molar. Let's see. We're going to be doing a stoichiometric calculation. Iron is 55.84 grams per mole, because you know we're going to be dealing with moles, but we want to end and we want grams of iron that are in the total mass. Let's see, and the mass, I'm going to put sub O for ore, is going to be 0.6128 grams. So these are our known quantities that will help us solve the equation. Now, the question is what is the reduction of manganese? That's a -1. So what? Oxygens are a -2. 4 of them is a total of -8. Of -8, so manganese has to be a +7. So manganese is going to be reduced from +7 to +2. So if you look at the question carefully, you were told what your half reactions already are. So we're just going to start there. Okay, so half reactions. If you want to put potassium in here as an ion, you can, but when you add your equations together and cancel what's the same on the left and right, potassiums will cancel out. And then your oxidation half reaction, so iron 2 becomes iron 3. Okay, so now irons are balanced, manganese are balanced. We can go straight to balancing oxygens. Okay, so the iron is not going to need any waters because it has no oxygens to balance. The permanganate has 4 oxygens. Oh, hang on. Which means I'm going to need 4 waters to balance those. Okay, and then the iron, of course, does not have to balance any oxygen. All right, so that's done. Now we use protons to balance the hydrogens. Again, no hydrogens in the iron equation, so we're just going to be working on the permanganate equation. Okay, so now let's make this a little more clear. There we go. Okay, so we have 4 waters, so that's 8 hydrogens. That means I need 8 protons on the left. And like we said, we're still fortunate the iron doesn't need anything. Okay, now we need to balance charges. So let's look at our permanganate equation. I have a +8 from the protons and a -1. Total charge of +7. Then water is neutral, then +2, so total charge of +2. So that means that the left is going to end up getting 5 electrons to make both sides a +2. The iron is pretty easy. You have a +2 and a +3. The right side is going to get 1 electron to make both sides a +2, which is going to make another one of our steps very straightforward. Okay, so manganate, 8 protons plus 5 electrons. Manganese 2 ion, and then your 4 waters. Okay, and then the iron. Now iron 2 is going to become iron 3 plus an electron. All righty. So now we need to balance the electrons. We have 5 electrons in the permanganate equation, 1 in the iron equation. So we only need to multiply the iron equation by 5 to match the 5 electrons in the permanganate equation. So make this easy on myself. I'm just going to carry this down. Okay, and then the iron equation. Multiplied by 5. That's going to give me 5 iron 2s, 5 iron 3s, and 5 electrons. So now I'm going to take this equation and this half reaction and add them together. Okay. Okay, and we notice again, 5 electrons are gone. They cancel. All righty, so manganate, 5 iron 2s plus 8 protons. Okay, so then we get manganese 2, 5 iron 3s, and then 4 waters. And we look and say, can anything else cancel? And it can't. So now that means our balanced redox equation is, again, we don't do the hydroxide step because this whole problem is in an acidic solution. So we only do the acid balancing. Okay, and now we have a balanced equation from which we can do our stoichiometric calculations, which, and of course, if you were paying attention, this is the same redox equation that I gave you a couple slides ago at the start of this section. I did that so you can check yourself as you're going through, but maybe you noticed that, maybe you didn't. So now, our mass percent is, remember, that's going to be the mass of iron divided by the total mass of the ore times 100. So we need mass of the iron in the ore. Okay, well, you have 38.37 milliliters. The permanganate solution is what was needed to fully oxidize the system. So this tells you uh, how much was needed to react all of the iron in the acidic solution. And that's going to be our key to figuring out how much iron is in the acidic solution. Change that into liters, because of course now milliliters divides out. And then our permanganate solution. So again, our potassium permanganate is 0.0198 molar. And if you think about that, potassium permanganate is a soluble salt, so it will fully dissociate into potassium and permanganate, meaning that whatever concentration the potassium permanganate is the same concentration of potassium ions and permanganate ions. So that means that I have 0.0198 moles of my permanganate per liter. And so think about that. Let's say I have two of these. Well, when they dissociate, I'm going to get 2 potassiums and 2 permanganates. That's why the concentrations also match. Okay, so liter is gone. Then I look at my equation, the redox equation we just balanced. I see 1 mole of the permanganate reacts in a ratio with 5 moles of iron. So iron 2, but from this point, we're just going to call it iron. And so your permanganate's gone. Well, moles of permanganate. And then we know that iron is 55.84 grams of iron per mole. So then moles of iron is gone. When you multiply this all up, you're going to get 0.212 grams of iron in the original sample, in the original ore. Now we can do this. Let's think, iron 2 is not necessarily neutral iron, but it was neutral iron. It was put in the acidic solution. It became iron 2. So it was iron metal, which is going to be a mixture of various, various isotopes and whatnot. But the reason we can say that the iron 2 is the same mass as the iron is because all that changes is the iron loses 2 electrons to become iron 2. Electrons are so tiny, they're not going to make a difference in the mass. The mass is dependent on the protons and neutrons, which doesn't change. So we can just switch back and forth between iron and iron 2. Okay, now mass percent. That is going to be the mass of iron divided by the total mass of the ore times 100. That is going to be 0.212 grams over the original mass of the ore was 0.6128 grams times 100. Our mass percent is going to be 34.6% iron in the original ore sample. So we do need to know how to balance redox in order to solve certain chemical reactions. All right, so this gets us through chapter 4. We'll be starting chapter 5 here, hopefully tomorrow, but we're going to get through chapter 5 and as much as chapter 6 as possible, because then next week you have exam 2. We'll play tomorrow by ear because I have to do some things. I have to make a budget for our new engineering program that's coming up. And so we'll see what we get done. All right, but this finishes off chapter 4. All right, talk to you later.